All right, welcome to The Explainer. Today, we're tackling a subject that, let's be honest, can seem a little intimidating, chemistry. But for the next few minutes, I want you to just forget about the complex charts and lab coats. Think of it like this. Chemistry isn't just a science, it's the language the universe uses to write absolutely everything, from the stars in the sky to the phone in your hand. So, let's dive in and learn how to speak it.
So, if chemistry really is a language, how do we speak it? Well, like any language you've ever learned, we have to start with the absolute basics. We're going to learn its alphabet, we'll cover its grammar, and then, finally, we'll put it all together to form complete sentences. Ready? Let's get started.
So here's our game plan. We'll kick things off with the alphabet, the basic particles of all matter. Then we'll figure out how we can possibly measure and count these tiny things. From there, we'll look at chemical formulas, which are kind of like recipes. Then we'll cover the unbreakable grammar rules that everything has to obey. And finally, we'll put it all together to write some chemical sentences.
First up, the alphabet. In the language of chemistry, the basic characters aren't A, B, and C. Nope, they are the fundamental particles that make up everything around us. We're talking about atoms, molecules, and ions.
So our most basic letter, our A or B in this chemical alphabet, is the atom. It's the tiniest possible piece of an element, like a single atom of gold or a single atom of oxygen that still has all the properties of that element. It's the fundamental starting point.
And once you have letters, what's the first thing you do? You start making words. And that's exactly what a molecule is. When atoms bond together, say 2 hydrogen atoms and 1 oxygen atom, they form H2O, the molecule we call water. That's our very first chemical word.
Then we have ions. Now these are a special kind of character. An ion is an atom or even a molecule that has an electric charge. You can think of that charge like a built-in exclamation point. It gives the particle a little extra oomph and totally changes how it behaves and interacts with everything else. Now, this is a super common point of confusion, so let's clear it up. Think of an atom as a single Lego brick. A molecule, then, is the cool spaceship or house you build with those bricks. A single oxygen atom is the brick. The O2 molecule that we actually breathe is the finished structure. All right, just 2 more quick vocabulary terms to round things out. A radical is kind of like a common phrase. It's a group of atoms that tends to stick together and act like a single unit. An atomicity sounds complicated, but it's really simple. It's just counting the letters in a molecular word. For water, H2O, the atomicity is 3. Simple as that. Okay, so we have our alphabet, but there's a huge problem. These letters and words are impossibly ridiculously small. So how in the world do chemists actually measure them? It's not like you can just pop a single atom on your kitchen scale, right? Well, this is where they got really clever. Instead of trying to find the actual mass, chemists came up with a brilliant workaround, a relative scale. They just picked one atom, carbon-12, and set it as the standard. Now everything else is just weighed in relation to it. It's kind of like saying a bowling ball is 16 times heavier than a baseball without ever needing to know the exact weight of the baseball in grams. And that same exact logic we apply to whole molecules too. The relative molecular mass is just the sum of the relative masses of all the individual atoms inside it. So, using our analogy, it's just the total weight of a word based on the combined weight of all its letters.
Okay, so we can weigh atoms now, which is a huge step. But that's only half the battle. For chemical reactions to work, you don't just need the right weight of your ingredients, you need the right number of atoms. So, how do you count particles when there are literally billions of trillions of them?
Now seriously, think about that for a second. It's a completely impossible task. So chemists developed one of the most important ideas in the entire field, a truly ingenious solution for counting. Instead of trying to count individual atoms, they decided to count them in gigantic groups. And this is the magic number. It's known as Avogadro's number. And just like we know a dozen always means 12, this number represents a specific quantity for chemists. It's an absolutely enormous number because atoms are so incredibly tiny. You can think of it as the chemist's dozen. And that special group, that chemist's dozen, has a name, the mole. Now here's the crucial takeaway. 1 mole of anything, whether we're talking carbon atoms or water molecules, always contains 6.02 times 10 to the 23rd of them. This concept, the mole, is the single most important bridge that connects the microscopic world of atoms to the macroscopic world of grams that we can actually see and weigh in a lab. So now that we can weigh and count our chemical letters and words, let's look at how they're actually written down. Chemical formulas are basically the recipes of chemistry.
They tell us exactly what ingredients are in a compound and, just as importantly, in what amounts. And there are two main types you'll see.
The empirical formula gives you the simplest ratio. Think of it as the basic recipe. For glucose, it's 1 part carbon, 2 parts hydrogen, 1 part oxygen. So CH2O. But the molecular formula, that tells you the actual number of atoms in one single molecule, the full scaled-up recipe. In this case, that's C6H12O6. As you can see, the molecular formula is always just a simple multiple of the empirical one.
Every language has grammar, right? Rules you have to follow? Well, chemistry is no different. There are fundamental, unbreakable laws that govern every single chemical reaction. You can't just throw elements together however you want, you have to follow the rules. So let's go over the 3 most important ones.
This is the big one. The law of conservation of mass. All it means is that in any chemical reaction, you have to end up with the same amount of stuff you started with. The atoms just get rearranged into new molecules. It's like you're just shuffling the same letters to form new words. Nothing is ever lost or gained.
This law basically says that a recipe for any given compound is fixed. Water is always made of 2 hydrogen atoms and 1 oxygen atom. It doesn't matter if you get that water from an iceberg in Antarctica or from your kitchen tap. H2O is always H2O. The proportions are definite.
Now this one sounds a little more complex, but it simply explains how the same elements can form different compounds. Think about carbon and oxygen. They can combine to form carbon monoxide, which is CO, or they can form carbon dioxide, CO2. For a fixed amount of carbon, the amount of oxygen it combines with will be in a simple whole number ratio, in this case a ratio of 1 to 2.
Okay, we have the letters, the words, our counting method, and the grammar. It is finally time to write some sentences. And in chemistry, our sentences are called chemical equations. They are the perfect way to describe exactly what happens during a chemical reaction.
So this is what a chemical sentence looks like. On the left side, you have the reactants. Those are your starting ingredients. On the right, you have the products. That's what you make. But the most important rule is that the sentence must be balanced. Look at the table for making water. We start with 4 hydrogen atoms and 2 oxygen atoms on the left, and we have to end with the exact same number on the right. Nothing is lost. It's all just rearranged. That is a perfect, complete chemical sentence.
So there you have it. We've learned the alphabet, the grammar, and how to write the sentences of chemistry. We've gone all the way from single atoms to fully balanced equations. The key takeaway here is that this isn't just a random set of rules to memorize, it's a powerful language that lets us describe, predict, and even create the world around us. And that leaves us with one final thought. Now that we know the language, what powerful stories can we write with it?